All right, so we're getting ready to start our next unit, which is Unit 4 on impulse and momentum. And quite honestly, in terms of equations, this is actually a very, very lax unit. Only a few different equations that we need to worry about. And it's primarily used when we deal with things like collisions. So anytime you see something hitting another object, impulse and momentum is typically what we get into as the best way to quantify it. And when I think about that, if an object's at rest, in order for me to get it in motion, there has to be some type of a collision. So even as simple as me pushing something, where did that velocity come from? Where did that kinetic energy come from, right? And that's what impulse and momentum gets into. So the first section is just a pre-lecture video on impulse and momentum. And in this video, he talks a lot about like kicking a ball. So he actually kicks this ginormous soccer ball, and he talks about how if we were to make a graph of the force exerted over time, it would look something like this. And but when he exerts that force, that's where that velocity comes from, and that's what actually starts this concept. Is impulse is where velocity comes from, but we got to talk about what exactly that means as it comes up. But the area under the curve of this force versus time graph is an object's impulse, which is the letter J, and we'll talk about that throughout this unit. So the first section, even though this section is really about momentum, and that's what it's typically referred to as, we're actually going to start by talking about impulse. And my Cliff Note 30-second version of impulse is a force exerted over time. It's a force exerted over time. Does that mean that's the formula for it? No, I probably shouldn't have done it like that, but it's a force exerted over time. It's actually force times time. And we'll talk about that this section. So anytime that if you want to get an object in motion, there has to be some type of collision. Collision, the physics sense, is just a short duration interaction between two objects. So when I kick a soccer ball, there is going to be a collision. And if you look at this high-speed slow-mo picture, you actually see that the soccer ball is around here. And when it collides, this kind of becomes flat. The ball, one side of the ball becomes flat, and that flatness causes a compression of the air. It also causes an elastic stretch of the material, and that causes the object to move. So during the time of the collision, it actually takes time to compress the object and then re-expand, and then depending on what type of material it's made out of, that'll affect how long it makes. But when you have that collision, that's what gets an object in motion. So here's an example graph of a force versus time of kicking a soccer ball. And we call the impulse force is the large force exerted during a short time interval. That is the area under this curve right here. And we use the letter J for impulse. I'm not really sure why. I always say I should look it up, but I never do. So anyway, the impulse is the area under a force versus time graph, or therefore it's the force exerted over time, which is F delta T. So that's the impulse, and where that comes, what we'll do with that, we got a lot that we'll do with it, but we'll just start with this for right now. So the impulse, the effect of the force is directly proportional to the area under the curve of a force versus time graph. Now, this might get a little tricky. Again, we're going to simplify things. If I have this first graph A, it's actually really tricky to calculate the area of this curve, the area under this curve, because it's not a easy shape. So what we do is we simplify it, and we just look at the average force exerted over time, and we say that's the force. Now with a soccer ball, that force changes as a function of time, but for right now, we're just going to keep it simple, and we're going to say that the force is constant, and then we're just going to look at the average force exerted over time. Okay, so here's a quick little demo. If I throw an egg against a wall or a hard board, obviously the egg's going to break. But in this other example, and I plan on showing this during class, the egg is thrown against a bed sheet. And when you throw an egg against the bed sheet, no matter what surface you throw it against, the egg has to stop. So would I rather throw it against the wall or would I rather throw it against the bed sheet? And the reason that this bed sheet doesn't actually break the egg is because it increases the time of the interaction and it decreases the force, although the impulse is the same in both conditions. So that's kind of a confusing thing, but we'll talk about it a lot in discussion. The impulse is the same, but we can variate, or we can help modify the force and the time. This is an interesting little video where this guy talks about the compression of a golf ball. So this is the title. This is the Pro V1. It's a very popular golf ball, but this guy is actually an engineer, and they try to always change and modify golf balls so they have a better flight pattern. They get more compression out of the ball, which causes a bigger velocity. So like all this stuff, and they go into the slow motion of hitting a golf ball. And it's actually really interesting. All right, so we got a quick check, and it says two 1 kilogram stationary cue balls are struck by the cue stick. So if you play pool, there's some impulse going on there. You're exerting a force over time. And which ball has a greater final speed? So hitting with 100 newtons for 2 milliseconds, or 20 newtons figures are not drawn to scale, but we have, 10 newtons. We'll say this is 10 newtons right here for 20 milliseconds. And the correct answer is both balls will have the same final speed because the areas under the curve are the same. So when we look at impulse in algebra-based physics, it's more useful to think of things as an average force and get the area under the curve. So we keep it constant and keep it easy. And that's just going to have, all it's simplifying is saying that the area under the curves are going to be the same for this option A and the option B, and then we can use our impulse equals the force exerted over time. So just using the area under the curve. So our impulse is the area under the first force versus time curve, or it's the average force times the time. Sorry for these boxes, but impulse has a unit of Newton seconds, which is also a kilogram meter per second. So we'll use kilogram meter per second for both impulse and momentum, and that'll make more sense when we talk more about momentum. So an impulse is a vector quantity which points in the direction of the average force vector. And one quick little note is this is actually going to relate to a little later. So force is also mass times acceleration. So we'll take a look at how these things relate in the future parts of this unit. So we do have a quick little example. Obviously we'll do it in class, but the rubber ball experiences the force. What's the impulse and what's the average force? So the peak force here is 300, so I'm also wondering what the average force is. So we're going to use the area under the curve to find the impulse, and then also use that impulse with the force exerted over time to figure out the average force. And we'll do that in class.